Last video, we talked about ways to check that polynomials of degree 2 or 3 are irreducible. And now I want to talk about a useful general technique for showing that a polynomial is irreducible that applies to polynomials of any degree. This is proposition 12 in section 9.4. Let's say that R is an integral domain, I is a proper ideal of R, and P of x is a non-constant monic polynomial in R bracket x. Okay, if the image of P of x in R mod I bracket x cannot be factored into two monic polynomials of smaller degree in this ring, then P of x is irreducible in R bracket x. So what's the idea? We reduce the coefficients of P of x modulo I. And if we get something that's irreducible in this ring R mod I bracket x, then the polynomial we started with was irreducible in R bracket x. And the thing that makes this work is this discussion from the very end of the last lecture. So remember, R is an integral domain that's not necessarily a UFD. So most of the last lecture was about proving that R is a UFD if and only if R bracket x is a UFD. But at the end, we said that when R is an integral domain, P of x, or a monic polynomial, a non-constant monic polynomial, P of x in R bracket x is reducible in R bracket x. If it's reducible, that implies that there are two non-constant monic polynomials, A of x and B of x in R bracket x, such that P of x is equal to the product of A of x times B of x. So if your polynomial in R bracket x, your monic polynomial, is reducible, then it is the product of two non-constant monic polynomials. And because the degree of P of x is the sum of the degree of A and the degree of B, and neither one of these degrees is 0, these are two polynomials that have smaller degree. So okay, you can start to see this statement about cannot be factored into two monic polynomials of smaller degree. Okay, so we're going to prove this statement arguing by contradiction. Let's suppose that you take P of x, you reduce all the coefficients modulo I, you get something in R mod I bracket x, and let's suppose that it cannot be factored in R mod I bracket x as a product of two monic polynomials of smaller degree. But let's suppose that P of x is reducible in R bracket x anyway. And let's find a contradiction, which will prove that, in fact, P of x was irreducible in R bracket x. All right, so let's suppose that P of x is reducible in R bracket x. That means that it factors in R bracket x. P of x equals A of x times B of x, with A of x, B of x non-constant monic polynomials in R bracket x. Okay? So let's reduce the coefficients modulo I in this expression. So we're looking at the image of P of x in R mod I bracket x and the image of this product A of x times B of x in R mod I bracket x. We know that this operation of reducing the coefficients modulo some ideal I, that's a ring homomorphism. So we get the image of A times the image of B. So this is giving us a factorization in this ring R mod I bracket x. So what's true about the image of A of x and the image of B of x in this ring is that these are polynomials in R mod I bracket x of the same degree. Why are they the same degree? Well, these polynomials are monic. So when we reduce the coefficients modulo I, what we get are still monic polynomials, and the degree is the same. That the leading coefficient in this reduce mod I operation, it can't go from being 1 to being 0. Like the degree of the image can't go down. So what we get are two polynomials that have the same degree. So because we had a factorization into non-constant polynomials here, we're also getting a factorization into non-constant polynomials in R mod I bracket x. And they're still monic because the identity, if you have 1 as your leading coefficient, you reduce modulo I, and you still have the coset of I containing 1. You have the identity in R mod I. Okay, so this is a contradiction because we assumed that the image cannot be factored in R mod I bracket x into a product of two monic polynomials of smaller degree. And by reducing the coefficients modulo I, we're getting exactly such a factorization. Okay, so there's really one idea that goes into the proof here, which is suppose that P of x is reducible in R bracket x, and then you reduce coefficients modulo I. So this proposition is really useful. And the idea is you have a polynomial in R bracket x, and you want to know if it's irreducible. If you reduce modulo some ideal I, reduce all the coefficients modulo I, and you get something that's irreducible in R mod I bracket x, in the sense that it cannot be factored into two monic polynomials of smaller degree, then it was irreducible in the bigger ring. So in the original ring, R bracket x. So one way to show that polynomials are irreducible, for example, in Z bracket x, is to reduce all the coefficients modulo some prime p and see that what you get is a polynomial that cannot be factored in Z mod pz bracket x. So I'll pause and erase, and I'll show you one example of this kind of reasoning. Let's consider an example. I claim that x squared plus x plus 1 is irreducible in Z bracket x. And the idea is we're going to reduce all of the coefficients modulo 2, and we get x squared plus x plus 1, but now considered as a polynomial in Z mod 2Z bracket x. This polynomial is irreducible in Z mod 2Z bracket x. Why? It's a polynomial of degree 2 in f bracket x for some field f, and it has no roots in f in Z mod 2Z. Just plug in 0 and plug in 1, the two elements in this field, and you see that you have no roots. So this is irreducible. And now this proposition says, okay, we started in an integral domain. We took this proper ideal 2Z. We took a non-constant monic polynomial in R bracket x. The image, when we reduced all the coefficients modulo I, could not be factored into two monic polynomials of smaller degree in Z mod 2Z bracket x, which means that the polynomial we started with was irreducible in Z bracket x. Okay, I'll say that this example, you can also prove that this is irreducible with proposition 11, applying the rational root test. If it were reducible, it would have to have a root in Q. The only roots you need to consider are 1 and -1, and neither one of them is a root. But I want to show you this technique because this ends up often being very useful for understanding when polynomials are irreducible.